Good morning, students. We will start now. Okay, so far we have discussed this much topics from unit number 1. So we have seen the definition of machine learning, then types of learning, then hypothesis space and inductive bias, and in the last lecture we covered evaluation techniques and cross validation. In evaluation, we have seen how to evaluate our generated model, and then in the last class we discussed cross validation. Today we will start with linear regression, our first machine learning algorithm. So we are going to start with linear regression. So as we know, regression comes under which type of learning? Supervised learning, right? Supervised learning. And there is a counterpart of regression, that is classification algorithms. There is one major difference between classification and regression. So in supervised learning we have x and y pair, right? So x are the given features, okay, or the inputs, and y are the output or the labels. Now in classification, this y, the output is discrete value, okay. Y is nothing but a function defined over the input features, right? Y is nothing but a function on x, f of x. So this y is a discrete value in case of a classification, and in terms of regression, y, which is nothing but a function of f of x, is continuous value. Okay, so y can have any value from the domain of y. Okay, so we'll start with one basic example. So how will be the relationship between the height and weight? Height versus weight. What will be the relationship of height and weight? Is it a positive relationship? Means if height increases, weight also increases? They have positive. Yes, they have positive relationship, right? So generally with the increase in height, okay, so we have height along the x-axis, okay, and weight. Okay, so with the increase in height, weight generally increases, right? So you will have, so consider I have collected a data of 1000 people, okay, so my data will exhibit this property. With the increase in height, there is a increase in weight. Okay, now we may have some people in this region. Now just think over these samples. What will be these samples? And we will have some people lying in this region also. Majority will exhibit this relationship, positive relationship, okay, but some people will be lying in this area, okay. We may have samples here also, okay, and some people will be here, okay. Can you tell me these people are what?
Outliers.
They are known as outliers, okay, but in this real world example, these are the
Exceptions.
yes, these are the obese people who are short in height, right? We may have these cases, okay, their height is less but they are obese people, okay, so they are real people, okay, they are not the errors in reading, okay. So we may have such samples also. And what about this? height is more but weight is very less. Okay, so they are very tall and thin people, right? They are not the miscalculation or error in recording. Okay, they are the real peoples. Okay, but they will be very less in number. Okay, they are very exceptional cases. Okay, and but general population will follow this trend, right? So either we can ignore the outliers. Okay, so they lie. Okay, they don't lie in the distribution, so that's why they are known as outliers. Okay, so we can ignore the outliers. Okay, or we have two counterparts, right? Okay, so they will nullify each other, and okay, so they will nullify each other and we will get this distribution only. Okay, and so now as you can see, there is a relationship, there is a positive relationship between these two variables. Okay, so now I can draw a line passing through the middle of this distribution. As my model or the decision boundary is linear in nature, so I can say that this is my regression line. Okay, this is my linear regression line. Getting the example, right? Okay, so that was my population. Okay, and that is my okay, so we have a regression line now. So see, this height is the independent variable. Independent variable, also known as a predictor. So given a height, I am predicting a weight. Okay, so this variable, okay, which is used for finding a regression line, is known as an independent variable or the predictor variable, and this variable is known as dependent variable or the response. Okay, weight is dependent on the height. Okay, that's why this variable will be known as dependent variable or also known as response to this predictor. Next concept is, okay, so now what we are trying to do, first, what is the requirement of linear regression? Your data should exhibit a relationship, either a positive relationship. So if a slope is positive, then you can say that we have a positive relationship. If slope is negative, okay, so if you have line like this, then you can say that the variables exhibit negative relationship. That is also fine, but there should be a relationship between the variables. Okay, so what we generally do, we find a correlationship between the variables. Okay, so there can be different cases. So case 1 is positive correlationship. Okay, positive correlationship is like this. With the increase in the independent variable, there will be increase in the dependent variable. Okay, so this is a positive correlationship. Co means what? Together, right? Co, together, and relation. Okay, so they exhibit some relation, and so this is an example of positive relationship. Case 2 is okay. Now the example of this is price and the mileage. Mileage means distance covered by the vehicle. Okay, so if your vehicle is old, that means mileage will be less, right? Distance covered will be more. Okay, then its resale value decreases. Okay, so that is the example of negative relationship or correlation. Negative correlation. Now, what about this distribution? Okay, so we have x and y. Now points are scattered all over this space, right? So there is no correlation. There is no correlation between these two variables. Now you cannot find a perfect line that best fits this data. Okay, you can come up with any line, okay, but that is not a good indicator of the relationship between x and y, because there is no relation at all, right? So the primary requirement of linear regression is there should be some relationship between the variables. That's why we first find out the correlationship. Okay, if the correlation is there, then we go for the regression. And here we are focusing on a linear regression. That means we are going to find a regression line. Okay, so that line generally represented as y equals to beta 0 plus beta 1 x. Okay, now we are focusing on a simple linear regression. We will be focusing on simple linear regression. Now just split the words simple. So we are considering only one feature. We will be considering only one feature. That's why we have only one x. Linear, we will have a line equation. That's why we remember a line equation, right? It is generally in the form of this: y equals to mx plus c. M is known as the slope and c is known as the y-intercept, right? Intercept. We have studied this in 12th standard, line equation, right? Okay, so linear means we will be having a linear model, and regression, so y will be a continuous value. Okay, so in today's lecture we will be focusing on simple linear regression. Now, so here using our given samples we have to learn which variables. Can you tell me? We have 4 variables here: y, beta 0, beta 1 and x. So from the given sample we have to learn which coefficients or which variables out of these 4. Just think over it. Y is the output. Okay, so consider we have this distribution. Okay, same example, height and weight. Okay, so x in this example, x is a height and y is a weight, right? So for the new person, let's say this is the height. Okay, so we'll be having a regression line. Okay, for this height, what is the corresponding weight value? So we'll go upwards, okay, and we'll return that particular y value, right? Okay, so x will be given for the given sample and y is the actual output, right? So we have to learn beta 0 and beta 1 from the given samples. Okay, so our ultimate aim is to find beta 0 and beta 1 value. Okay, so now let's try to find out the values of beta 0 and beta 1. Okay, so let me redraw the samples. So we know that there should be some relationship between the x and y. Okay, so as you can see, my data points are lying in this range. Okay, so this is the range of x, right? And this is the range of y. Okay, now one thing I can infer from this sample is my regression line must pass through x bar and y bar. What is x bar? X bar is the mean of x and y bar is the mean of y. Okay, which will be here. Okay, so see, this is the range of x, so this will be my x bar, right? Okay, and this is the range of y bar will be in the middle of that. Okay, so this is my x bar and y bar. Okay, so my observation 1 is regression line must pass through through x bar, y bar. Okay, x bar and y bar are the mean of x and y respectively, right? Next thing, okay, so if we know, so my line equation is y equals to beta 0 plus beta 1 x. Now consider if we know the value of beta 1, okay, and this line is passing through x bar and y bar according to our observation, right? So this line equation must satisfy for this point, right? Okay, so if I have put these values in this equation, so I can get a value of beta 0. Beta 0 equals to y bar minus beta 1 x bar. Okay, so this is the formula of beta 0. Okay, so we can clearly find out the value of y bar and x bar from the given samples. Okay, so consider if we have 100 given samples, okay, so we will have 100 points. So let's say 2, 3, 3, 5 and so on. Okay, so these are the x values, these are the y values. Okay, so we can easily find out x bar as 2 plus 3 plus 2 plus 3 plus and so on divided by 100, and y bar equals to 3 plus 5 plus divided by 100, right? Now one thing is remaining is how to find out the beta 1. Okay, we'll have a formula for finding beta 1, that is correlationship between x and y into the standard deviation of y divided by standard deviation of x. Now we will not go into the mathematics of this equation, okay, but using this formula we can determine the value of beta 1. Okay, now so let's revise what we have studied till this moment. So our variables may exhibit positive relationship or negative relationship. Okay, so our ultimate goal is to find that particular line that best fits the data, right? Okay, now the x variables are known as independent variables or the predictor variables. Okay, y are known as dependent variable or the response of that predictor. Now some examples are given. Positive relationship, so we have seen weight versus height, they exhibit positive relationship, or salary versus years of experience. Okay, so as years of experience increases, salary generally increases. Then marks obtained versus number of study hours, right? Now negative relationship, price versus mileage, price versus production. If production is more, price will be less, right? Marks obtained versus Facebook usage, right? So they exhibit negative relationship. Now we have different types of regression. Okay, I missed that point. So different types of regression model. Okay. Now when you consider only one feature, that model is known as simple one. Okay, and if you have 2 plus features, 2 or more, that is known as multiple regression, and your regressor can be a linear one or non-linear one. Okay, so we have linear, non-linear under both the categories, linear, non-linear. Okay, so till now we have focused on only linear regressions. Okay, so you may have a non-linear regressor also. For example, if your pattern or the distribution is following a sinusoidal distribution. Okay, so your regression will be a sinusoidal. Okay, so you may have a non-linear regression line. Okay, so we'll be focusing on the linear regression only. Okay, under this unit. Okay, so when you have one feature, that type of regression is known as simple regression. So you may have linear or non-linear regression line, and under multiple also we have the same category. Okay, so now what will be a prediction error? So that prediction error is indicated in red line. Okay, so for this line, okay, consider for this sample the actual value is this one. Okay, let me draw. The actual value is this one, but our model has predicted this value. Okay, because we'll be returning that value, right? So difference between these two will be the error, prediction error, right? And the actual value is this one, right? But our model has predicted this value. The difference is in those two values will be our prediction error. Okay, so based on that we'll be having different metrics. Okay, we have studied few like mean absolute error, sum of squared error, right? So we will be finding the difference between the actual value and the predicted value. Yes. So our line equation will be in this form y cap. So cap is actually represents the predicted value. Okay, cap. So beta 0 plus beta 1, sorry, beta 0 plus beta 1 x, that is our line equation. We have to learn this beta 0 and beta 1 value. We have observed that regression line has to pass through x bar comma y bar, that is mean of x and mean of y. And beta 1 is given by this formula, correlation of x and y multiplied by standard deviation of y divided by standard deviation of x. Now if you simplify, so I will show you the formula of correlationship. Okay, so this is this one. Just quickly I will write it here. Summation n xi minus x bar y bar divided by square root of summation I equals to 1 to n xi minus x bar and summation I equals to 1 to n yi minus y bar square. Okay, so I have the equation of correlation here. Okay, now we'll be having n samples, so that's why our summation is going from 1 to n. Xi is the current sample, x bar is the mean of xi. Okay, so xi is the mean of all the x, and the formula of standard deviation is this one. Summation I equals to, I am writing small n to keep the consistency, and instead of mu is the mean, I will be writing x bar. Okay, now so this is a standard deviation for x and standard deviation of y, 1 by n summation I equals to 1 n yi minus y bar square. Now the formula of beta 1 is correlationship of x comma y into standard deviation of y divided by standard deviation of x. Okay, now if you put the values and if you simplify the equation, you get this formula of beta 1. Okay, some terms will cancel out and you get this simplified formula for beta 1. Okay, so you can easily calculate x bar and y bar from the given samples. Okay, for the given x, okay, x will vary from 1 to n. Okay, so by that we can find out the beta 1 value. Then we have derived the formula for beta 0, right? We have derived this formula for beta 0. Okay, so by that we'll get this line equation, because beta 0 and beta 1 is known now, right? So we can predict the value of y for the given sample now. Okay, and these are some measures for finding the error. We know, we have discussed mean absolute error, right? Y hat is the predicted value, y is the actual value. Okay, take a difference, that will be the error. Do it for all the samples and divide by n. Okay, so it is a mean absolute error. We have discussed sum of squared error also, right? Instead of taking absolute value, you square it. Okay, so there will be no problem of the sign of subtraction. Okay, that is a sum of squared error. Okay, similarly we may find SEE value, that is standard error of the estimate, and we'll discuss these two measure in next class. Okay, and the widely used metric is R square error. Okay, so I will tell you the significance of R square value. It varies from 0 to 1 in the next class. Okay, so any doubt in linear regression? Just try to understand the concept from the term itself, linear. So it will be a linear model. You have to find a line. Okay, that line is going from the x bar and y bar. Okay, so from that we got beta 0 value. Now how to find out the beta 1? So we have a mathematical formula for finding the beta 1 value, that is given by this one, and this is the simplified value formula for that, right? We know the line equation now, right? So for the given unknown sample, just put the values and you will get a output value. Simple, right? So any doubt in today's lecture?